Hello, grade 9. We're going to delve into topic 4 today, which is all about both pollution, pollutants, and concentrations. The title of this topic is How Much is Too Much? It's an interesting topic. It's also your introduction to a big thing we talk about in Chem 20, which is concentrations and kind of a little bit of background. We don't do any of it in Science 10, but we do a ton of it in Chem 20. So this is a good intro to that as well. It's kind of a tough concept. So what you're going to learn today, two things. You're going to describe and illustrate processes by which chemicals are introduced to the environment or their concentrations are changed, and apply and interpret measures of chemical concentration in parts per million, parts per billion, or parts per trillion, which is how we normally deal with concentrations of pollutants. This doesn't really work in this format where normally we would kind of have a bit of a conversation, but these are some terms we're going to define as we go through. So it'd be neat actually for us at the end to see if we can define them properly. But we're going to look at the following terms: pollution, pollutant. I said that weird. Pollutant. There we go. A little bit better. Toxicity. And then lethal, what lethal means, and specifically in the context of a lethal dose or LD50 value. So let's talk first of all about pollutant versus pollution. There's a big kind of difference here. A pollutant is any material or form of energy that will cause harm to a living organism. Okay, so it's like a specific thing. So we could talk about carbon dioxide as a pollutant, or methane as a pollutant, or we could even talk about light as a form of energy as a pollutant, because different light can actually be harmful to living organisms. For example, in a city when lights are always on. Sound pollution is another one. We're going to get into it, but that's another pollutant, excessive sound. Pollution is a alteration of the environment producing a condition that is harmful to living things. So when we talk about pollution, it's like the state of things. So if we say that a city has a lot of pollution, we're saying that there are many pollutants present which are causing harm to living things, or just one pollutant present, but it's kind of like the state or what's happening to the thing. It's the condition. So pollution is an effect of pollutants. So as we have pollutants present, then we call that pollution. So hopefully that makes sense. So if we take a look at a few pictures, these are some pictures of kind of both pollutants and pollution, right? So we see pollution as a state in the bottom, as we have a bunch of smog and the air quality is poor, while we have pollutants coming from smokestacks up above. We have, and it looks like some kind of a refinery type process there, and large amounts of pollution coming from that, or I should say pollutants, and then resulting in pollution as a result. So, can you name the 7 kinds of pollution? This is kind of an interesting thing because sometimes we don't think of different pollutants actually as pollutants at all, whereas pollution, we think that it's just kind of like something else or harmless. So the 7 types of pollution that we should know about is pollution in air. So we have things released to air that are harmful to living things. Pollution of water, right? So if we have water and different things in the water, which we're going to talk about a lot today, then that would be pollution. Pollution of land. So when we talk about, for example, as things get into soil and stuff, we have radioactive pollution, which is going to be a big problem as time goes on. That's a whole other interesting topic, and it might be something that we take a look at for like a Bill Nye video later on, of how they're building all these things to store nuclear waste, but they're all just designed of like, oh, this will be good for a few hundred years, but the things will remain radioactive for far longer than that. So it's just like, well, we don't have the technology to deal with that now. So that's a problem for generations down the road. We have noise pollution, which is just any noise that again can harm living things, and this would be a problem in areas that have a lot of noise, like a big city. Light pollution, we already talked a little bit about that, and then thermal pollution, which is not something that we talk about a ton, but actually heat and changes to the amount of heat being given off by different areas can actually change as well, or harm living things. A great example is actually in cities. it stays much warmer at night than it does in other areas. And that's often because the asphalt is absorbing sun during the day and then it's releasing it at night. And that actually heats up things in the nighttime. So thermal pollution, not something we think about a ton. You can actually see thermal pollution, for example, with our power plant in Medicine Hat, where the water gets released from the power plant. I don't know if you've ever been in that area, kind of by the river, but the water gets released by the power plant, and that water is a lot warmer than other water. And if you take a look at that area, you're going to actually find a huge amount of like algae growing and stuff because of the warmer conditions in that area. So it's actually changing what can live in that area, and it would be harmful to many living things that would live there otherwise. So talking about pollution, we're going to talk about our global footprint calculator, which ties directly into pollution and how much pollution that we actually cause. So this is going to be kind of neat. Follow the link, go through the questions, and see what your global footprint is. So in other words, how much space does it take for you to be able to kind of like live the way that you do from Earth? So we think about that as our footprint based on how much energy we require, how much food we require, and how much of the Earth's surface then would be required in order for us to keep things the way they are for us to have the standard of living that we do. That'd be kind of interesting. I might post in the Edpuzzle link my number so that you can see it and compare it to me. So let's talk about concentration. This is where we're going to spend the bulk of our time today. Concentration of a substance is often represented as a percentage, and what concentration is it's how much of a solute, okay, so a thing that's like dissolved, we have within a solution. So that could be, for example, water solution, where water is the solvent that's dissolving the stuff, or we could be talking about this with air. Okay, so we're talking about how much of a certain thing we have in the air. These are all different concentrations. So it's how much of something we have per larger amount of solution of a mixture. So percentage is one of the ways that we're going to talk about concentration today. It's a really easy way to understand. If we talk about yogurt, for example, that's a 1% fat yogurt. So to apply to milk too, then that means that out of every 100 grams we have of the yogurt, 1 gram is fat and the other 99 grams is other stuff. So 1% of it is going to be fat. And we're not worried about what the rest is, we just care about what we're talking about. So we're talking about the solute of fat, so we say that it's a 1% fat. So like it says here, and I already mentioned, if we have 100 grams of yogurt that we eat, we have consumed then 1 gram of fat and 99 grams of other stuff, whether it's solutes or solvent or whatever, it's whatever else is in the solution. So we're just talking about the specific solute in that case. Percentage is neat and useful. We use it a lot for things like, for example, alcohol, right? Alcoholic beverages is all about percentages. When you look at like a beer, it's like 4 or 5%. If you look at like vodka, it's like 40% alcohol. So that means that 40% of what's in there would be ethanol, and then the rest would be other stuff, primarily water. When we talk about something like hydrogen peroxide, 3% hydrogen peroxide, then that means that 3% of it is H2O2, and then 97% of it is other stuff, again, mainly water. Milk, I already talked about. What else? What else could we talk about for percentage? I'm kind of drawing a blank on that. Vinegar. Vinegar could be a percentage, like 5% vinegar, that sort of thing. So we do use percentages for concentration, but it doesn't work great when we have incredibly low concentrations. So for example, if we're talking about the amount of mercury that was in a lake, and we said that there's 0.0001% of mercury in that lake. That's not a great representation. It doesn't make a ton of sense. So because it's such a small number, it would be better represented by a different method. And for that, we've got a few different methods based on how dilute that is. And we have ppm, which is called parts per million. That's the largest of the units. So what that means is how many parts per million parts we have. And it's based on mass. So if I had 1 gram of mercury for 1,000,000 grams of water, it would be 1 part per million. Part per billion is even smaller still. So for things that are even more dilute, that's 1 part per billion parts. And then parts per trillion is smaller still. So if I add 1 gram of mercury for 1,000,000,000,000 grams of lake water, then that would be a part per trillion. So this works really well for pollutants, ones that maybe are harmful, but in very, very low concentrations, and we have to track how much we have. So just kind of an example here in this infographic thing, just how small is a part per million or a part per billion. In one Olympic-sized swimming pool, we have 660,000 gallons. So if we had 1 part per million in that pool, that'd be 1¼ 2-liter bottles. And if we had 1 part per billion in that pool, it would be half a teaspoon. And yes, we can track concentrations that low. We have technology now to track incredibly small concentrations of different pollutants or solutes. So parts per million is what is used most of the time for concentrations in environmental chemistry. It's a unit we use very, very often. And that's 1 milligram of solute per kilogram of actual solution, or typically water or air or whatever. So that might not make a ton of sense because you might not know like a milligram versus a kilogram, but milli means thousandth. So like millimeter is 1,000th of a meter. So when I have 1 milligram, that is 1,000th of a gram. In other words, it is 0.001 grams. And then a kilogram is 1,000 grams. Kilo means 1,000. So when I have a kilogram, I have 1,000 grams. Well, I can actually fit 1,000,000 milligrams into a kilogram. That's why it's a part per million. Okay, so if I take the amount of milligrams I have of a pollutant, of a solute, and I divide it by how many kilograms I have of solution, I can find my ppm. So 1 part per million means that 1 unit of chemical can be found in 1,000,000 units of solution. And you can figure out then what it would be for parts per billion, parts per trillion. We already talked about that. So just to put this in context, here's some information about different substances that are toxic in drinking water, and then the maximum acceptable concentration of what I can have. So basically, it's how much could I have in the drinking water without it being, based on guidelines, harmful to humans. So for arsenic, it's 0.025 parts per million. Incredibly small. Now, a good question is, what would that be in parts per billion, based on what you know? And the answer is it would be 25 parts per billion, because there's 1,000, right, millions in a billion. When I have chromium, I have 0.050 parts per million that's allowed in drinking water, so that'd be 50 parts per billion. Fluoride, 1.5 parts per million. Lead, 0.010. Mercury, incredibly harmful, so it's only allowed in a concentration of 0.001 parts per million. In other words, 1 part per billion. And then titanium is 0.02. So kind of interesting to see what's allowed. You can probably find information, I'll see if I can link it, of what the concentrations of different things are in drinking water. It's something that's monitored all the time. So maybe we can actually find local information. If I can, I'll link it here, of what's in Medicine Hat's drinking water in terms of analysis in parts per million, parts per billion, parts per trillion of different pollutants. That would be neat to see. Here's the formula for calculating parts per million. You're going to be doing some of this. Now, you won't be manipulating the formula. You're just going to be calculating concentration in ppm. And we're going to go through some examples of this so you can see how it works. So to calculate concentrations in ppm, I take my mass of solute, I divide that by my mass of solution, and then I multiply it by 1,000,000. Now, in this scenario, we're talking about solute and solution being in the same unit. So whether that's in grams or kilograms or milligrams or whatever, we have to have that in the same unit, and then we multiply by 1,000,000. Now, the other option for this formula that I talked about already is, instead of doing the same unit, I could do milligrams for solute and kilograms for solution. And the reason why this works, and then I don't have to multiply by 1,000,000, is because there are 1 million milligrams in a kilogram. So there's 1 million of these in a kilogram, which means I do not have to then multiply by 1 million because I'm already factoring that into the units I'm using. So kind of a neat shortcut. Here's a use of ppm. This is an interesting graph. This is the CO2 concentration from the, I'm going to say this wrong, it's in Hawaii, Mauna, yeah, Observatory. And this is a really high up observatory that does some air tracking as well, and it's tracked the CO2 concentration. And you can see basically how carbon dioxide has changed over the years and continually gotten larger. And this is one pollutant that we track in parts per million. So when I have a concentration, and this goes up to, what is this, 2015, 16, whatever. So let's say I'm almost at 400 parts per million here. So that means that if I took 1 million grams of air, okay, 1 million grams of air, 400 grams of that 1 million grams of air would be carbon dioxide, is basically what it means. Or if I took a kilogram of air, I would have 400 milligrams, 0.400 grams of carbon dioxide mixed in there. So it is kind of interesting to see the application. This is, the scale is not 0 here, it's 310, but going from 310 to 400 is, basically a 30% increase to the amount of carbon dioxide in the air, which is major. That's a lot. So carbon dioxide, one thing that's tracked, methane, and even worse, greenhouse gas, 50 times more potent than carbon dioxide, is also something that is obviously tracked in terms of greenhouse gases. And yeah, interesting. We'll probably talk about that kind of stuff later on. So I want to get into a few examples of this so you can see how it works. And these examples will be in your notes with solutions, so you don't have to necessarily copy it down. But if you do want to try this out, I'll get you to try out the second and third one and guess an answer. That would be great. I'm also going to walk you through a little bit of the process that I want you to use for problem solving, for doing number type problems. We're going to be doing more number type problems when we get into electricity, quite a few actually. So it's good for us to build some good habits now that we can use later. So I'm going to also introduce a little bit of symbols that are different that are in your notes. I didn't love these symbols here. I'd rather this be an M and an M, okay, to represent that it's a mass. And I like writing this out as CPPM, meaning concentration in ppms. So that's what we're going to use here. So I'll walk you through the process. You accidentally spill 4.5 kilograms of gasoline. That's a lot of gasoline to spill accidentally. But you spilled it into a lake that has this many kilograms of water, actually a small lake, 8.9 million. Calculate the parts per million of gasoline that you now have in that lake. So here's what we're going to do. We're going to start by writing out the variables of what we have. So the 4.5 kilograms is what we have of the solute, the pollutant. So M solute is equal to 4.5 kilograms. M solution, how much we have of the lake water, is equal to this number right here, the 8.9 million. So 8,900,000 kilograms of water. And what we're looking for here is my concentration in ppm. That's my question mark. Now, because these are both in the same unit, kilograms and kilograms, I'm going to use the formula that multiplies by 1 million. So I'm going to go ahead and go CPPM is equal to M solute divided by mass of solution times 1 million. One shortcut for writing out 1 million is we see that this is 6 zeros in 1 million. So we can always do instead 10 to the power of 6, which is shorthand for 1 million and easier in our calculator. So we make sure we don't miss a zero. But for some of you, exponents are a little bit scary. So I'm going to always kind of just do the million instead so we don't have that as a hang up. So let's try plugging in our values and see how this pans out. So I have 4.5 kilograms. You'll notice I showed the original formula here first that I'm using with the variables, and now I'm plugging in the numbers so that you can see the progression that I'm going through, and then I'm multiplying that by the million afterwards. So now I'm going to bring my calculator over here, and let's plug this in. So I have 4.5 kilograms. I don't put in the unit at all. The unit is the same, which is why we're using the formula involving the million. Then I have 8,900,000. Okay, I like pressing enter here just to kind of like go through that first step. Then I'm going to multiply that by the million. 1, 1, 2, 3, 4, 5, 6. And I end up with 0.505. So the concentrations in ppm is equal to 0.51 ppm. I have 0.51 because I am rounding this 5 up, right? So the 0 here rounds up to a 1 because the number after it is 5 or above. So I have 0.51 ppm, and we actually use that unit of ppm when we represent a concentration in parts per million. So that's the answer to the first one. Here's the next question. I'll move my calculator over just a tad. Actually, I'll move it off screen for now. Calculate the ppm for 0.200 grams of mercury and 1,500 grams of water. So again, we have the same unit. So we're using the formula where we were going to go ahead and, well, I'm going to show you two ways for this actually, but you're going to go ahead and use the million formula. So why don't you try this out? Give it a quick try, grab your calculator, see if you can get through it and find a final answer. So here's the solution. I'm going to first write out what I have. So I have m of solute is equal to 0.200 grams. And then I have m of solution is equal to 1,500 grams. And I'm looking again for my ppm. Concentration in ppm is my question mark. So I have C ppm is equal to m solute over m solution times 1 million. So my concentration in ppm is equal to 0.200 grams divided by 1,500 grams multiplied by that million. So let's go ahead and plug that into the old calculator and see how it pans out. 0.200 divided by 1,500, and that gives me this number, but now I have to multiply it by the million. And I get 133 ppms. It's a lot. It's a lot of ppms. Okay, another way to do this, if I instead wanted to use milligrams and kilograms, there's 1,000 milligrams in a gram, so that's 200 milligrams. And then there's 1,000 grams in a kilogram, so this is 1.500 kilograms. So I could instead just do CPPM is equal to 200 milligrams divided by 1.500 kilograms, and not multiply by the million because the million is built into the difference between milligrams and kilograms. And I would end up with 200 divided by 1.5, 133. The exact same answer, but a little bit less numbers involved, a little bit less scary in my mind. But for some of you, the changing of units is really tough, and you'll want to stay away from that. So I'm giving you the option of that method of milligrams and kilograms. You certainly don't have to use it. Okay, next question, question 3. Calculate the ppm for 0.0098 grams of DDT in 2,200 grams of water. So let's again walk through this. I have an M solute, which is the DDT, of 0.0098 grams. I have M solution equal to 2,200 grams of water, and I'm looking for my concentration in ppms, of course. So concentration in ppm is equal to M solute divided by M solution times 1 million. So C ppm is equal to 0.0098 grams divided by 2,200 grams times the 1 million. Okay, here we go. 0.0098 divided by 2200 multiplied by 1 million. And I get an answer of 4.45. Let's just go with 2 digits here. CPPM is equal to 4.5 ppm. This is another one where it'd be really easy to use the other method. Okay, so I could instead just say, well, 0.0098 grams, that's 9.8 milligrams. And 2200 grams, that's 2.2 kilograms. So I could just go 9.8 milligrams divided by 2.200 kilograms gives me my ppms. And if I do that, 9.8, wrong place. 9.8 divided by 2.2 gives me the same answer, 4.45. So that, again, would be a little bit of a shortcut in my mind, but you have to be strong at being able to change those units. So not for everyone. Okay, let's now delve into toxicity, which is kind of a separate topic that we talk about in relation to concentration. So toxicity is the ability of a chemical to harm an organism. The more toxic something is, of course, the more harm it can cause to the organism. We have 2 types of toxicity. Acute toxicity, which is immediate, it happens right away. And then we have chronic, which happens over time. So acute toxicity is when symptoms occur after only one exposure to the chemical, and it can do harm to you right away. So an example is methanol. Methanol is a type of alcohol that is very poisonous. It can make you go blind, and then it can kill you, obviously. So sometimes people accidentally consume methanol because of trying to make moonshine and making it improperly, or because they don't know about different types of alcohol and they drink methanol thinking that it's the same as ethanol, which is the kind in alcoholic beverages, and it's very toxic stuff. It's really, really bad. Funny enough, the treatment for methanol poisoning is actually just giving the person a ton of alcohol, normal ethanol alcohol, which actually binds to the same kind of receptors and prevents the damage from methanol. So that's acute toxicity, is something that does damage right away. Chronic toxicity is when the negative health effects happen over time as the chemical accumulates to a specific level in the body. So it's repeated exposure over a long period of time. An example of this would be lead. As you have lead in your body and it builds up, then it's going to cause more and more issues and problems in your body. So it's chronically toxic. So important to know those 2 terms. That kind of term of acute versus chronic is used all the time. When you talk about chronic pain is pain that lasts a long time, right? Like it's not going away. It's always kind of there. So terms that we use in life. So measuring toxicity, when we talk about toxicity, normally we talk about it as an LD50. So this is a good way of representing how poisonous something is, how toxic something is. An LD50 is the amount that it would take to kill 50% of a population. And it's represented in how much mass it would take for that chemical per kilogram of body mass of whatever's having it. So LD50 is the amount of a substance or dose required to kill 50% of a population to which it is exposed to. So normally when we talk about stuff, we measure it in milligrams per kilogram of body mass. Interesting enough, that's actually basically ppm. So it's how much ppms it would take to kill something. But that's a unit, it's milligrams per kilogram of body mass. So the higher the number, the less toxic the chemical is, because it takes more to kill the thing. So if you deal with something that, well, here's a good example. Nicotine has a LD50 of 0.86 milligrams per kilogram. So that means that for every kilogram of body mass, it takes 0.86 milligrams of it to kill 50% of the population. So let's say that you weigh 100 kilograms, okay? So that would work out to, it's pretty heavy, 220 pounds. That means that for 100 kilograms, it would take 86 grams of nicotine, or 86 milligrams of nicotine in order to kill off 50% of the population if everybody took the same amount. It is more toxic than caffeine, which is 130 milligrams per kilogram for the LD50. So it would take for a 100 kilogram person 130 milligrams. Sorry, cancel that. It would take 13 grams of caffeine, okay, to basically kill off 50% of the population. So another way of saying this is maybe you've got a 50% chance of surviving if you took 13 grams of caffeine as a 100 kilogram individual. I feel like I just made that more confusing. Anyways, moving forward. So looking at nicotine, if you gave the LD50 amount to rats of 0.86 milligrams per kilogram, so, based on the size of the rat, it might be a larger or smaller dose. So for larger rats, they're getting a little bit more. Smaller rats are getting a little bit less. So it works out to 0.86 milligrams per kilogram of body mass for the rats. How many would survive the dose if 2,400 rats were given that amount of nicotine? And the answer is you would expect that 1,200 would survive, okay? Because the LD50 means that 50% of the population would die at that specific dose. And this is actually how LD50s are determined. It's a little bit dark. They feed it to rats and mice until they keep on upping the dose until 50% are dead. And then that's how they figure out what the LD50 would actually be. Okay, so this is kind of an interesting question, a really good one. So here's different LD50s for chemicals. Some of these you might actually be familiar with from the pesticide project, but rank these from most dangerous to least dangerous. So most dangerous are the things that are the lowest LD50 number, which means it takes the least amount to kill 50% of the population. So this is by far the most dangerous. The second is this, strychnine. Solanine would be third, and chlordane would be fourth, excuse me. So that would be the order of highest to lowest toxicity, or most dangerous to least dangerous. So we're going from lowest LD50 value, because that means it takes the least amount to kill 50% of the population, to highest, which means it takes way less. So, I mean, for example, let's say we're talking about salt. Would you expect salt to have a high or a low LD50 value compared to, let's say, this stuff? And the answer is it would have quite a high LD50 value because it's much less toxic. So, an acceptable risk. Government agencies and legislative bodies are often pressured to relax the strict testing required before a new drug or substance is approved for everyday use. Do you agree with this thinking? Do you think that government should be involved in, regulating testing and how much can be in stuff, and going through all these LD50 calculations and major testing that must take place before a product is released? Well, an interesting question. I'm not going to answer it because that's an opinion piece. It's something to think about. There's always groups that are trying to lower the amount of testing that's actually occurring because it costs money and it costs delays. But it's an important part of the process. And without it, I think that there would be a lot of harm that's done that could be avoided with proper regulations. So that's my opinion, but you might have a different one, and you're certainly entitled to it. So risk to humans for a substance is difficult to determine from what we talked about with LD50 because toxicity testing is not done on humans. They don't give humans stuff until 50% of a population dies, because that would be murder and it's horrible. This is going to sound bad. There used to be testing that occurred in prisons, and this would be for human testing for different cosmetic products or like hair products or whatever, where they would give it to prisoners in exchange for small amounts of money. And that obviously stopped because it was very bad and caused like skin burns to prisoners and stuff. Interestingly enough, they were upset when, the majority of prisoners were upset when the ability to be involved in this kind of testing went away, because it was a chance for them to make money in the prison. But yeah, kind of fascinating. There was a podcast that I might link that I listened to about this kind of prison testing that occurred, kind of a very dark thing that no longer is happening, at least not in Canada or the US. False assumptions. Humans react the same to a chemical as a lab mouse or a rat. So we make that assumption that the LD50 we determined from feeding it to mice or rats is going to be the exact same as when we give it to humans. But this is an assumption, and it very well could not be true, right? It just really depends. Toxicity depends on type of exposure. So skin contact is less toxic than inhalation or ingestion. So it depends on how we're actually exposed to the product. And we don't account for that a lot of the time. So when we talk about how much could be involved in, let's say, or how much of a product could be in a shampoo, right? Then that's based on what it's used for, which is going on your hair. And it would absorb a little bit into your skin through your scalp, but we're not counting on you ingesting it. But then if a little kid comes along and thinks that the shampoo smells delicious and then eats it all, well, then it's not tested for that, and that's an issue. So this is another problem that can happen in terms of evaluating risk to humans. And the other thing is that everyone's different. So some people that wouldn't react, like, what am I trying to say? That some people would be way more sensitive than the general population to a specific substance. So as a result, the toxicities that are determined might not apply to everyone because everybody's different in their, bodies, immune systems, everything else, and the enzymes they have present and stuff. A lot of the things that we talk about in terms of toxicity that are toxic is because they actually affect enzymes and keep them from working properly in our body. And then that's the issue that causes us to die. So a great example of something where proper testing didn't take place was thalidomide, which was used for morning sickness in the 50s and 60s. So this was a drug that went through testing in mice and rats and stuff. And then they released it to the public as a morning sickness remedy pill during the 50s and 60s. The problem is it actually caused birth defects that resulted in very short and not properly formed limbs. So a lot of kids were born with these horrible birth defects because of thalidomide being used as a drug. And the problem actually had to do with the fact that thalidomide is something called an enantiomer. So thalidomide, just kind of like your right hand and your left hand, don't superimpose over each other, right? They're mirror images of each other. So they are, identical kind of ish, but they're different. They're mirror image. I hope that's making sense. I can't superimpose the two, right? My thumb lines up with my pinky. So the thalidomide is the same. There are two enantiomers. There is the R and the S variety. You can think about it as like the right hand and the left hand. Anyways, when they produced thalidomide, and this did not have any effect in rats, but when they produced it, they produced a mixture of the two. So both of these were present, this one and this one. This one is actually okay. It doesn't cause birth defects. This one does. So this one is the one that actually caused all the hassle, the S enantiomer. And as a result, because that was involved in the pill, there was a lot of the S enantiomer, then that's what caused the birth defects. Thalidomide is actually now used again as a drug. It's prescribed under a completely different name. I don't know what the name is, but it is simply this R1 that does not cause the same problems. So it does not cause the birth defects. But this is because there was not proper human testing. It was tested on rats and mice. It didn't have the same effect, but it did have the birth defects effect on humans. So that's why now drugs must go through clinical trials. They must go through testing with small groups to see what the effects are before they move on to actually releasing it as a medication. And it's got to go through quite a bit of clinical trials, which is, it's a good process in order for the same kind of thing to not happen again. And you're going to watch kind of a video on thalidomide. All right, so for review, let's quickly go back, hopefully I'm not making you dizzy, to this slide right here of do we now know these different terms? So pollution, right, is kind of like the state of having a lot of pollutants present that are harmful to living things. Pollutant is a certain substance or energy that causes the state of pollution, that causes harm. Okay, toxicity is how harmful something is to living organisms, and then lethal is death. So when we talk about lethal dose, it's the amount that's required to actually kill something, and an LD50 would be the amount that's required to kill 50% of a population. So that's what we talked about today. We also went through concentration in ppm, parts per billion, parts per trillion. You learned how to calculate concentrations in ppm, which is something we're going to do quite a bit of practice on. And yeah, that's it. That's the lesson. All right, have a good rest of your day.